Welcome back to the deep dive. Today we are strapping into one of the most mechanically demanding and frankly dirtiest environments on Earth, the concrete mixer truck.
And we're not just talking about its driving dynamics. We're getting into the really complex task of electrifying the mixer itself.
Exactly. Our sources for this deep dive are truly unique. It's a highly detailed set of functional specifications, really an in-depth technical research report prepared in a consultancy style.
It's essentially a playbook. It maps out the entire architecture for an engineering team that's developing a P2 hybrid plus an electric power takeoff system for a new generation of these cement mixer trucks.
So the mission here, as it's laid out, is to transition this heavy-duty workhorse from, an inefficient, high-emission machine into something that's economical, silent, and critically functionally safe.
Right. We're basically uncovering the entire engineering strategy. How do you design a system that not only gets you over 30% fuel savings, but also survives in one of the harshest environments imaginable?
And while complying with the absolute peak of functional safety, ASID.
Which is no small feat.
Okay, so let's unpack this a bit. Before we get into kilowatts and silicon carbide, we have to understand the fundamental problem. What makes electrifying a concrete mixer truck so different from, say, a regular long-haul cargo truck that just drives down the highway?
That distinction is everything. For a long-haul truck, the biggest energy challenge is pretty straightforward: acceleration and maintaining speed on the road.
Right.
For the concrete mixer, though, the critical difference isn't the driving at all. It's the duty cycle. The report defines this as the long-duration, low-speed, high-load parking mixing operation.
So the truck spends a huge portion of its life just sitting still, but its main job, the mixing, is running at full tilt. That just sounds like a recipe for massive inefficiency in a traditional diesel system.
It is. And the technical report really emphasizes this pain point because it dictates the entire hybrid architecture choice. We have to detail this mixer duty cycle, which is, well, it's far more punishing than just stop-and-go traffic.
So what does that cycle look like?
The first and most defining mode is parking mixing. This is continuous operation for a really extended period, often 30 minutes, but it can easily stretch to 90 minutes straight.
90 minutes.
90 minutes. And this demands high, consistent torque at low drum speeds. This leads to two specific risks: mechanical overheating of traditional hydraulic parts, and for any power electronics, a massive, sustained thermal accumulation risk.
And you're doing this in high heat, high humidity, with a constant spray of cement dust, and I imagine some pretty harsh concrete cleaning agents. That whole environment is just inherently corrosive.
Absolutely. Then you have the second mode, which is agitating mode. It's during transport. Now, the power demand is pretty low here, maybe 5 to 12 kilowatts. It's just enough to keep the concrete from separating.
But it's still continuous?
It's still continuous. The drum never stops spinning while there's concrete inside. So even when the truck is moving, the generation system has to be active. And then finally, you have the mixing mode. This is the high-speed phase, usually during the initial loading or that final high-viscosity discharge.
This is peak load.
This is peak load.
Yeah.
It requires a continuous power output somewhere between 40 and 60 kilowatts.
Yeah.
Just to handle that dense, thick concrete slurry.
So with the conventional approach, that massive diesel engine has to idle that entire time just to spin the drum through a mechanical power takeoff. That really explains the economic disaster they're trying to fix.
It does. I mean, that traditional pain point is the justification for this whole project. Relying on a diesel PTO means incredibly high idling fuel consumption. The source material quotes some astounding figures.
How bad is it?
Up to 30, sometimes even 50% of the total fuel consumed during a shift is spent just sitting still, mixing concrete.
That's like running your SUV at highway speed for hours just to charge your phone. The waste is just colossal.
And it gets worse. There's an environmental impact that's specific to the engine's after-treatment system. Because the engine is idling at such a low load for so long, the exhaust temperatures are too low. When the temperature is low, the chemical reaction needed to, convert nitrogen oxides and burn off soot, it just doesn't happen effectively.
So the filters get clogged.
Exactly. You get frequent, rapid clogging of the diesel particulate filter, the DPF, and the selective catalytic reduction system, the SCR. And that means higher maintenance costs and more downtime for the vehicle.
So the goal isn't just about moving the truck silently in a city, that silent discharge capability, but it's about solving this fundamental duty cycle problem, aiming for a consistent 30% or more in fuel savings by electrifying the process.
Precisely. And that necessity leads directly to a very specific architectural choice, one that can decouple the mixing power from that horribly inefficient diesel idling cycle.
Okay, so the technical report is very clear about the solution to this whole parking mixing dilemma. It proposes an architecture that completely decouples the engine from the mixing function, turning it into a pure power source. What's the recommended technical route, and how does it stack up against other hybrid layouts?
The analysis strongly recommends the independent PTO APU, that's auxiliary power unit generator, combined with a high-voltage DC bus. The report defines this as a series hybrid or a range extender, a REEV configuration.
And that's a critical decision, right? Driven entirely by that operational profile we just talked about.
Entirely.
So let's quickly run through the other options that the source material looked at, just to understand why they didn't make the cut.
Sure. The primary rejected option is a P1 ISG setup. That's where the generator is directly connected to the engine's crankshaft.
Why was that a non-starter?
It's dismissed outright because the source notes it would suffer from just severe diesel engine torsional vibration. That's the massive mechanical pulse you get every time a cylinder fires. Plus, you'd face power limitations because the diesel engine's crank speed isn't always optimal for generating high power.
Okay, and what about a P2 architecture, where the generator is mounted at the rear and you can decouple it with a clutch?
P2 is technically feasible, but the report finds it's just too mechanically complex. It would require significant changes to the chassis, and that makes it expensive. For a commercial vehicle that's laser-focused on low total cost of ownership, that complexity is a huge liability.
Which leaves the independent PTO, or APU, as the optimal solution. Tell us why it wins out.
Well, it's optimal because it allows for complete mechanical decoupling from the drive shaft and the transmission. The diesel engine, which is now just acting as a power source, is physically separated from the drivetrain. It's only connected to the generator.
So the engine can just run in its happy place.
Exactly. It can operate permanently in its most efficient range. Its brake-specific fuel consumption maps sweet spot at a constant high-efficiency RPM. This optimizes fuel use while generating full, consistent electrical power for either mixing or charging the battery. It's really the only way to guarantee those big fuel savings during that long parking mixing cycle.
Now, this brings up a huge strategic question for any high-voltage system. The source specifies a 400-volt platform, defining it as 250 to 460 volts DC. The premium passenger car world is all moving to 800 volts. Why stick with 400?
This raises a really important distinction between engineering vehicles and, high-performance passenger cars. The short answer is reliability, ruggedization, and TCO, in that order.
Total cost of ownership.
Right. Cost sensitivity is paramount for commercial vehicles where the margins are incredibly tight. The 400-volt supply chain is just incredibly mature globally for these heavy-duty, high-current components. We're talking high-power pumps, reliable DC to DC converters, all the ancillary stuff.
So using 400 volts just leverages this existing low-cost, high-reliability infrastructure.
Absolutely. The infrastructure is cheaper and it's proven. But even more critically, the source emphasizes reliability in that harsh environment.
Right. The humidity, the vibration, the cement dust.
Exactly.
Yeah.
All those factors increase the risk of an electrical short because of surface contamination. So engineers have to increase what's called insulation and creepage distance.
Which is the physical distance electricity has to travel across a surface to cause a short.
Precisely. And 800 volts makes that problem exponentially harder.
It does. At 800 volts, the required creepage distances are far greater. That means you need larger components, more complex potting compounds, much more expensive insulation materials, all of which have to withstand the chemical attack from those concrete cleaning agents.
So staying at 400 volts allows the system to be fundamentally more compact, more robust, and more reliable in the long term, especially in that brutal working environment. The engineers here really prioritized ruggedization and uptime over marginal charging speed gains they might get with 800 volts.
That feels like the ultimate commercial vehicle engineering trade-off. Durability and proven reliability win out over future charging speed trends.
It is.
Okay, let's move to the heart of the system, the generator. The choice here is between a permanent magnet synchronous motor, a PMSM, and an asynchronous machine, an ASM. What makes PMSM the clear winner for this kind of continuous high-torque application?
Well, what's fascinating here is how that specific duty cycle again forces the engineering team's hand. They have to choose a higher cost component because the alternatives just can't meet the operational demands.
So even though the asynchronous machine is cheaper and avoids the whole rare earth magnet supply chain risk?
The permanent magnet synchronous motor is deemed the only reasonable choice.
Okay, why? Give us the 4 key performance factors the report hinges on.
Okay, first, power density. A PMSM is 20 to 30% denser than an ASM. You have to remember, we're mounting this unit in a tightly packed engine bay on a chassis that's already loaded with auxiliary systems. Compact size isn't a luxury, it's a necessity for just fitting it in.
Right. Second.
Second, efficiency. This is where the TCO calculation really comes to life. A PMSM peaks above 96% electrical efficiency. Now, that crucial 2 to 4% advantage over the best ASM might seem small in a lab.
But over thousands of hours.
Exactly. Over the lifespan of a system that's continuously generating, maybe 2,000 hours a year just mixing concrete, that translates to hundreds, if not thousands, of liters of diesel saved. It's a massive total cost of ownership benefit. The efficiency literally pays for the premium cost of the motor.
It does. Okay, what's third?
Third is low-speed torque. A PMSM inherently provides superior torque characteristics at very low speeds. This is essential for the initial startup phase and for managing the substantial resistance of that mixer drum, especially when it's full of high-viscosity concrete that's maybe settled a little bit.
And the fourth, which you said was the most crucial.
All right. The fourth, and most crucial for the entire architecture, is dynamic response. The permanent magnet motor allows for a much faster, more precise magnetic response. And this fast response is absolutely critical for enabling that high-performance active damping feature we'll talk about. It's the necessary solution to the whole torsional vibration problem of this architecture.
So an ASM just can't respond fast enough for that kind of sophisticated control.
It simply can't. It doesn't have the bandwidth.
Hmm.
So the decision for PMSM isn't just about maximizing efficiency. It's about enabling the core control strategy that prevents the system from tearing itself apart mechanically. It's really an enabling technology wrapped up in a high-efficiency package.
Without it, the whole independent APU architecture is potentially just unviable due to durability concerns.
Exactly right.
So let's talk raw power. How powerful does this generator actually need to be to meet those high load demands of continuous mixing?
Well, the targets are derived from needing to cover everything at once. Peak mixing loads, powering the hydraulic pumps, running the air conditioning, and charging the battery, all simultaneously.
Okay.
So the required continuous power, what they call S1 continuous duty, is specified as at least 120 kilowatts. And this has to be achievable while the engine is in its sweet spot, so typically 1,800 to 2,200 RPM.
And peak power.
They also need a peak power capacity for transient loads, something lasting 30 to 60 seconds, of at least 160 kilowatts.
160 kilowatts. That is a serious amount of power for a component that's just bolted onto a truck engine.
It is. But look at the torque requirements, because this really reveals the brutality of the application. The rated continuous torque is around 550 newton meters. But the source material highlights the cold start peak torque requirement.
Which is?
At least 900 newton meters.
900. That's not just for handling a bit of sticky concrete. What is driving that enormous transient torque demand?
It's a dual-purpose requirement. First, yes, it's the initial resistance when you're trying to start that mixer drum from a dead stop with a heavy viscous load inside.
Right.
But second, and perhaps more fundamentally, that huge burst of torque is needed when the ISG acts as the starter motor. It has to overcome the immense physical compression resistance of a massive, heavy-duty diesel engine.
Forcing those big pistons through their compression stroke.
Exactly, before the diesel combustion can even initiate. Standard automotive starter generators operate at much lower torque levels. 900 newton meters is just the sheer mechanical leverage required for this class of engine.
That 900 newton meter figure, it really emphasizes the engineering scale we're talking about. It's a generator that has to be as strong as a Super Duty starter motor and as efficient as a high-end power plant.
That's a great way to put it.
Okay, now let's move to the GCU, the Generator Control Unit. This is the brain that manages all this power. And here's where it gets really interesting, because the report advocates for a big strategic transition in power electronics. The move to silicon carbide, or SiC, MOSFETs, over traditional silicon IGBTs. Tell us why they're making this crucial and, I'm guessing, costly investment.
This is maybe the most significant technology decision outside of the architecture itself, and it's a necessary one. The report provides a really rigorous technical and economic justification for it. The core job of the inverter is rapid, highly efficient switching.
Right, turning DC from the generator into AC for the motor and vice versa.
Exactly. And traditional silicon IGBTs are really reaching their theoretical limits, particularly when it comes to heat generation.
And silicon carbide resolves that heat problem.
Drastically. First, you get a massive switching loss reduction. Silicon MOSFETs reduce switching losses by an astonishing 70 to 80%.
70 to 80.
It's a physical effect. Sikiki eliminates what's called current tailing, where the IGBT continues to dissipate energy as heat for a tiny period after you tell it to switch off. Less energy lost as heat means significantly less heat generation overall, and that's vital for a system that's already struggling with external heat in a packed engine bay.
So lower losses means better system efficiency, but also it's just easier to manage all that external heat.
Precisely. Second, look at switching frequency. Siki allows for switching frequencies in the 20 to 60 kilohertz range. IGBTs are typically stuck down at 4 to 10 kilohertz.
And that high-frequency capability is not just about making the current waveform smoother.
No, it is the physical prerequisite for high bandwidth, high performance control. Which brings us right back to active damping. You need that frequency for fast feedback loops and responsiveness.
Got it. Third point.
Third, thermal management. Because CKD generates so much less heat internally, and because it has superior thermal conductivity, you can actually reduce the size of the liquid-cooled heatsink by 30 to 50%.
And that's not just about saving space.
No, it's about minimizing the surface area that is constantly getting blasted by cement dust and those harsh alkali cleaning agents, which are a constant threat to cooling performance and long-term reliability.
Okay, let's tackle the big challenge. Assembly modules are expensive. They're typically 1.5 to 2 times the cost of IGBTs. How do you justify that initial price tag in a cost-sensitive commercial vehicle market?
That's the core of the engineering justification. Total cost of ownership, TCO. While the initial module cost is higher, the analysis in the source material shows that the system-level efficiency gain, that continuous 2 to 4% extra efficiency, pays back the premium in a surprisingly short operational time frame.
Because the system is running nonstop.
Right. Given the vehicle's non-stop fuel-intensive generating lifespan, the diesel savings alone make the TCO of the Siki system better than the cheaper IGBT alternative. It's a clear case of spending more upfront to save exponentially more on operational costs.
The economic case for SCU in a system that runs continuously for an hour or more at a time is it's inescapable.
Indeed. And now, armed with that lightning-fast response capability from SEEK, we can finally get back to the key differentiator, active damping.
This is the technology that makes the whole independent APU architecture viable, right? This is what allows them to remove the traditional heavy mechanical flywheel.
Correct. So the P1 APU architecture relies on a direct mechanical coupling between the engine and the generator. Since the massive flywheel, which normally acts as a big inertia sink to absorb torque pulses, is removed, the diesel engine's discontinuous combustion creates severe torsional vibration.
And if that's left unchecked?
If that massive plus or minus 50 Newton-meter ripple is left unchecked, it causes major noise, vibration, and harshness NVH issues, and critically, it leads to rapid transmission durability failure.
So active damping is essentially electrical noise-canceling technology, but for mechanical vibration. How does the control logic actually work?
It's an incredibly sophisticated control loop that's operating in milliseconds. The GCU uses a high-precision resolver sensor mounted right on the engine's crankshaft to monitor the crank speed ripple.
So it's watching the tiny instantaneous accelerations and decelerations from each cylinder firing.
Exactly. And the GCU software then calculates and rapidly injects a counter-phase electromagnetic torque command.
Like injecting an opposite wave to cancel out the noise?
That's a perfect analogy. This counter-phase torque is opposite in phase and magnitude to the engine's torque pulsation. So when the engine is at a mechanical torque peak from a combustion event, the GCU instantly increases the electrical load on the generator to absorb that peak.
And when it's in a valley between firings?
It reduces the electrical load or even briefly motors the shaft to fill that valley. It's continuously shaving the peaks and filling the valleys using the instantaneous magnetic force of the PMSM.
Which is why the fast response of the Supervisory power electronics is so critical. You need that bandwidth to keep up with the engine's internal dynamics.
Precisely. And the results from the report validate the technology. The engineering validation showed this active damping strategy reduced the output shaft torque ripple from that severe plus or minus 50 Newton meters down to an astonishingly stable plus or minus 8 Newton meters.
Wow.
That stabilization dramatically improves NDH, it protects the entire transmission line, and it ensures the long-term durability of all the system components.
That really is the core enabling technology. Now, beyond active damping, the GCU has to manage transitions between all these various operating demands generation, voltage control, torque control. What are the key control modes and, just as importantly, the thermal management strategies?
The GCU has to function as a truly dynamic power manager, and it switches seamlessly based on what the VCU is demanding.
So mode 1 is standby.
Right, standby, it's just monitoring system health, the high voltage interlock loop, the DC bus voltage. Then you have mode 2, the voltage control mode. This is critical for stability. The GCU maintains the DC bus voltage at a very precise target, say 400 volts.
Why is that so important?
Well, if the battery is disconnected or malfunctioning, this mode ensures that critical auxiliary components, like the power steering pump, still get stabilized power. It's the definition of a limp home capability.
Makes sense. And when the engine is actively generating for the mixing operation?
That's when you're in mode 3, torque control mode, which is where active damping primarily lives. It's all about stability and suppressing those engine fluctuations. And then there's mode 4, generation mode, where GCU is simply commanded by the VCU to deliver a target power output like 120 kilowatts for a continuous operation.
Okay, let's look at the dark side of all that continuous power, heat. The thermal dearing strategy must be incredibly robust, given the continuous high load.
It's the primary protection against catastrophic failure. The design specifies a hard stator winding temperature limit of 145 degrees Celsius.
And the GCU software enforces that.
It implements protection logic that mandates clear, graduated action. So if the temperature exceeds 155 Celsius, the GCU has to enter a Diderot state, where it linearly reduces the maximum current and power output to manage the thermal load.
And if it keeps getting hotter?
If the system continues to overheat and the temperature goes above 170 degrees Celsius, it must trigger an immediate mandatory shutdown. It sets the torque limit to 0 and reports a critical fault. Those temperature thresholds are hard-coded safety limits.
It's amazing that software has to perform the job of a mechanical fuse, just constantly monitoring and mitigating potential thermal runaway.
It's the only way to do it safely.
Okay, moving from performance and thermal management to safety. Any high-voltage system with this kind of power output demands compliance with ISO 26262. And we're not just talking about meeting regulations. We're talking about designing a system from the ground up to prevent catastrophic failure. How does the GCU get to that highest level of automotive functional safety?
The system requires compliance up to ASIL-D, which is the highest automotive safety integrity level. And ASIL-D is reserved for hazards that have the potential for a fatal or catastrophic outcome. The Hazard Analysis and Risk Assessment, or HARA, process identified 3 core hazards that necessitate this rigorous approach.
Let's break down those 3 critical hazards from the source material, starting with the most serious one.
Hazard 1 is the highest priority: unintended high-voltage electric shock. The HARA rated this S3E2C3.
Okay, let's define those terms for the listener.
Sure. Severity S is S3, meaning fatal injury is possible. Exposure E is E2, meaning exposure to the hazard is likely. And controllability, C, is C3, meaning the driver or technician would have difficulty controlling the situation to prevent harm.
And that high rating of S3 and C3 makes ASIL-D mandatory. The safety goal is just absolute HV safety.
Absolute. Hazard 2 is excessive unintended generation torque. This is rated ASIL C or D. If the control unit fails and commands a massive uncontrolled torque output, say 500 Newton meters when the engine is running, it could cause sudden, violent vehicle instability or literally destroy the drivetrain components.
So the safety goal there is simply to prevent unintended torque.
Correct. And finally, hazard 3 is generation overvoltage, which could cause a battery fire or damage. That's rated ASIL C. If the GCU fails to regulate its output, the DC bus voltage could spike dangerously high, threatening thermal runaway in the battery or damaging other critical components. The goal is to prevent the DC bus voltage from ever exceeding safe limits.
That paints a very clear picture of the stakes. So how do engineers design an electronic architecture that meets that ASIL-D requirement, especially for the high voltage shock and the unintended torque hazards?
The solution is what's called ASIL-D decomposition. You can't rely on a single processor or a single software loop to guarantee ASIL-D. The design has to use a primary and a monitoring architecture, a dual-path system.
So we're talking about true redundancy.
Yes, mathematically, acyl D is achieved by decomposing the function into two independent paths, so acyl BD plus another acyl BD.
So what does that look like in practice?
It means the primary functional path, which manages the active damping and the power output, is monitored by an entirely independent safety path. This usually runs on a separate processor core, maybe with a different compiler or even different sensor inputs, to achieve what's called diversity.
And that monitoring unit is constantly double-checking the math.
Constantly. It samples the resolver sensors and recalculates the actual torque demand independently. And if it detects a mismatch, a serious one,
What happens then?
if the actual torque deviation exceeds a severe safety threshold, the report suggests around 50 newton meters, which would signal a massive runaway. The monitoring unit directly executes safe torque off, or STO.
An STO is a hardware mechanism, not software.
It is a hardware mechanism. It's not a software command. It's a physical relay or a gate cutoff that immediately suppresses the firing signals to the power devices, completely independent of the main software loop. This guarantees the torque is zeroed out, fulfilling that safety goal.
That's a critical hardware layer of defense. What about the high-voltage safety mechanisms designed to protect, say, maintenance staff or emergency responders?
Those are managed by two mandated mechanisms. First is the high-voltage interlock loop, the HVIL. This is a low-voltage circuit that runs continuously through all the high-voltage connections, the connectors to the battery, the GCU, the motor, even the battery lid.
So if any of those connectors are disconnected accidentally or violently.
The HVIL circuit is physically broken, and a break must result in a power shutdown within 100 milliseconds, as specified by the ECE R100 standards. It's the first line of defense against accidental contact.
And the second mechanism,
The second is active discharge.
making the bus safe.
Precisely. Active discharge is required because the high-voltage bus stores energy in its capacitors, and that can be lethal even if the source is cut off. So, upon detecting any major fault, a collision, an HVIL break, an internal fault, the GCU has to immediately and actively dissipate that stored charge, bringing the HV bus voltage down to below 60 volts within 5 seconds.
And that ensures that emergency personnel touching the chassis or components after an accident aren't exposed to lethal voltages.
Exactly.
This level of detail really confirms that functional safety isn't an afterthought. It's intrinsically linked to every component choice, right down to the fast switching of the CO. So, what does this all mean for system communication? How do all these different controllers, the VCU, the battery management system, the GCU, talk to each other seamlessly and safely?
They all communicate over the vehicle's central nervous system, the SAE J1939 CAN bus, running at 500 kilobits per second. This is the standard backbone for heavy commercial vehicles.
But because this is a specialized hybrid system,
Right. Because it's specialized, the report strictly mandates the definition of proprietary parameter group numbers, or PGNs, to avoid conflicts with the thousands of standard engine and transmission messages already flying around on the bus. For example, the report defines proprietary ranges like 0 by 18 FF1001.
can you highlight the most critical messages for power management?
Sure. The Vehicle Control Unit, the VCU, sends the GCU command. This is the instruction set for the generator. It includes vital signals like the GCU enable flag, the current mode generation, voltage control, torque control, the target power in kilowatts that the VCU needs, and the target DC voltage that's being requested by the BMS.
And in return, the GCU is constantly reporting back its operational status.
Yes, the GCU status message reports the system's actual performance, actual power output, actual torque generated, the precise DC bus voltage, and the current GCU state, like faulted, ready, or running.
And there's a heartbeat signal.
Critically, every system broadcasts GCU heartbeat. This is just a simple counter signal, but it is absolutely critical for ISO 26262 communication supervision.
So if the heartbeat stops, the VCU assumes the GCU has failed.
Exactly. The VCU has to continuously monitor that heartbeat, and if the signal times out, the source specifies a maximum timeout of 1,000 milliseconds, the VCU must assume the GCU has failed and trigger a fail-safe action, which would likely mean initiating active discharge and reporting a severe fault.
Finally, how do they manage the diagnostic data, which is essential for engineering investigations after a failure?
The system has to adhere to standard J1939 diagnostic protocols. The GCU must immediately report active faults, that's diagnostic message 1, or DM1, and record historical faults, DM2. And critically, safety faults like HVL fault or inverter overtemp trigger not just a shutdown, but also the recording of a freeze frame, a DM18 snapshot.
What information does that freeze frame capture that makes it so vital?
It freezes all the key operating parameters at the exact microsecond of the fault. the battery voltage, the engine speed, the commanded torque, the internal temperatures, the current control mode, everything. This frozen data is absolutely necessary for the rigorous 8D root cause analysis process that's required for any severe safety incident. It allows engineers to determine exactly why the system failed.
It connects that abstract concept of functional safety directly back to standard shop floor diagnostic procedures.
It does.
That was a tremendous deep dive into the GCU. But the source material introduces another new controller that's vital to the mixing operation, the SCU, or Superstructure Control Unit. Now, this seems to complicate the architecture. Why introduce another ECU? Why can't the vehicle control unit just handle the mixer drum logic?
This raises a really important question about control responsibility in electrified commercial vehicles.
Yeah.
I mean, in the past, the mixing logic was simple relay logic activating hydraulic pumps.
Right.
Now, with electrification and all these ASIL mandates, the VCU and the mixing system operate on fundamentally different timescales, and they have competing safety focuses. You can't merge them effectively without compromising the VCU's primary mission.
So define that boundary for us using the report's logic.
Okay, there's a clear VCU versus SCU boundary. Think of the VCU as the car's brainstem. It's managing basic survival. The VCU, the vehicle control unit, manages driving torque, vehicle safety like ABS and traction control, and it operates on a very fast millisecond-level timescale for dynamic control. Its focus is keeping the vehicle stable and drivable.
And the SCU.
The SCU is more like the prefrontal cortex, managing the complex task. It oversees the entire mixing and discharge state machine, all the logic for loading, transit, and unloading, and the safety of the upper structure. It operates on a slightly slower 10 to 100 millisecond timescale.
So the SCU's job is making sure the mixer operates safely, including protecting against things like accidental tipping.
Exactly. The SCU is the necessary safety gatekeeper for the upper structure. It handles safety issues that are unique to the mixer, like tilt sensor monitoring, preventing drum reversal at high speeds, and making sure the loading chute is stowed correctly before the truck moves.
And if you tried to put all that complex, high-level mixing logic into the VCU,
You'd risk VCU task overload, and critically, you would blur those clean ASIL safety boundaries.
so the coordination between them has to be highly organized.
It's strictly hierarchical. The SCU requests the power it needs from the VCU and says, I need 60 kilowatts for high-speed mixing. The VCU then grants the allowed power based on the overall vehicle status, the current battery state of charge, and charging limits.
So if the battery is too hot or the engine is in a protection mode, the VCU can just say no.
It can deny or reduce the power grant, and the SCU then has to manage the mixing process accordingly with the power it's been given.
We've engineered the system for performance and safety. Now we have to validate it. Given the severity of the operating environment, what does the comprehensive validation and test plan, the DVP&R, look like for this generator and controller unit?
Well, the environmental durability has to meet the most rigorous, heavy commercial vehicle standards, which is the ISO 16750 series. This is really where the theory meets reality.
Let's start with the mechanical loads. We know the ISG is mounted directly to the engine, which is the most violently shaking place on the entire vehicle chassis.
The mechanical loads testing has to be brutal. They have to pass ISO 16753 Test 7, which covers the severest vibration spectrum for engine-mounted components. This means cycling the unit through engine-specific sine wave vibration, so low frequency, high amplitude, and random road vibration high frequency simultaneously.
All while cycling the temperature.
All while cycling the temperature from minus 40 C up to plus 125 C. This testing ensures the structural integrity, the connector reliability, and crucially, the fatigue life of the PCB solder joints will survive millions of engine cycles.
And we mentioned the chemical environment, cement dust, alkali cleaners, urea. How do they test against that?
The chemical loads testing is mandatory and extremely specific, following ISO 1675055. The testing has to include extended immersion and spraying cycles with the common chemical loads found on site. This specifically requires exposure to concrete cleaning agents, which are strong alkalis or acids, and the urea solution, DEF or AdBlue, from the SCR system.
And the housing and sealing materials have to survive that for years.
They have to. Finally, the functional testing has to prove that the new technology's SiC and active damping work flawlessly.
And that requires specific high-fidelity testing.
It does. First, you have efficiency MAP validation on a dynamometer to confirm the GCU and motor actually achieve that critical 96.5% peak efficiency and the high operational efficiency you need for the TCO payback. Second, and critically, there's mandatory hardware in the loop. or HIL testing.
Why is HAL mandatory here?
HIL testing simulates the exact nonlinear dynamics of the diesel engine and the electrical load in a controlled lab environment. This lets engineers confirm that the active damping algorithm can robustly reduce the engine's torque ripple by over 70% under every conceivable simulated scenario: cold start, rapid load change, the long-duration mixing cycle.
And they can do all that before they risk testing on a physical prototype, which could be destroyed by an uncontrolled torque ripple.
Exactly. HIL is the safety net for the most complex control loops.
So, wrapping up this comprehensive blueprint, what's the final critical path summary for the engineering team? What are the key milestones that determine the success of this project?
Well, the conclusions are very clear. The independent PTO-PU is the required architecture. PMSM paired with the cycle seat GCU provides the optimal balance of performance and durability. And mandatory HLCD safety compliance is completely non-negotiable.
And the development path?
The critical development path really involves 4 simultaneous steps. Step 1. Establish the motor efficiency MAP and the corresponding thermal model. This dictates your supplier selection and your cooling system design. Step 2. Complete the GCU safety architecture in all the ISO 26262 work products, especially the ASIL-D decomposition and the HRE documentation.
Right.
Step 3. Build and rigorously test the HIL test bench to validate that active damping algorithm and all the safety mechanisms, like STO and the active discharge logic. And Step 4. Execute long-duration, real-world durability testing that's focused on that extreme, continuous parking mixing cycle. Mastering these areas is the pathway to success.
We've charted this journey from a really simple engineering problem, a concrete truck idling and wasting fuel, to a highly sophisticated safety-critical system that's relying on bleeding-edge size technology. It's just remarkable how the unique, continuous, high-torque duty cycle of a cement mixer truck completely dictates every single component choice.
It really does. It forces the adoption of high-cost, high-performance technology like SIX and these high ASIL safety standards just to achieve efficiency and survive the application.
What's fascinating to me is the trade-off calculus at the heart of commercial vehicle engineering. They chose the proven 400-volt platform for its cost and inherent reliability in that corrosive environment, yet they realized they couldn't skimp on the 6A power electronics.
Right. The efficiency gains needed to justify the entire hybrid investment demanded the best switching technology. And that torsional vibration problem necessitated the high-frequency response that only SIX could provide to make the whole mechanical decoupling architecture function. The solutions here are just so deeply interconnected and mutually dependent.
It's a beautifully complex system. It demonstrates that innovation often occurs not in the perfect environment, but in the most demanding ones. Thank you for walking us through this deep dive into power electronics, functional safety, and heavy vehicle architecture.
It was a pleasure to explore this technical blueprint.
And for you, our listener, here's a final provocative thought to mull over. We discussed how the GCU must implement active damping, a sophisticated electrical mechanism to smooth the diesel engine's mechanical torque fluctuations. If a future, pure battery electric mixer truck without any internal combustion engine naturally eliminates these complex torsional vibration issues entirely, how might the engineering team need to fundamentally redefine its functional safety and control priorities, given that its biggest mechanical headache is simply gone?